What? Where's the recording? Recording has started. I want the recording to start.
Wait a second part. For the quiz, you're supposed to read the page like
Pause.
145 on his line.
Okay, class, let's begin. If you guys have your notes out, let's get your notes out and stuff, and let's finish this up here. So you guys did this on the calculator, true? So we learned that, dun, da, da, da. We learned that if you have numbers like this, and let's kind of rewind a little bit here. So if you have like a -3 on the outside of your function, right? You pretty much you have a horizontal change because it's the x-axis. We're good.
Because I'm putting it on the inside.
And if you have a +1, and that is a y change, that means you're going to go up 1. We're good. So notice these guys are your horizontal change and your vertical change. We're good. Just so you know. And then this 3 here, you guys talk to me. What does this 3 do for our function? Notice that. And then let's go back to our graph here. Boom. What do you think is the 3 that's doing something here? So hold on real quick here. So the -3 that we did, right? It moved it to the left, right? And then what happened? We moved up. That was the -3 at the end of our function. And that was the +1 at the end of the sine function.
Wait, so how do you move down?
Oh, you just go, let's see. I figure if you want to move down, you just put -1 over here, right? Remember, because this controls all your y values, right?
Wouldn't that be negative? Okay.
And
It's
this
the X
guy,
and the Y. Okay.
yeah,
I didn't see it was X. Okay.
this guy would control all your horizontal stuff.
Yes.
Right.
That.
So
Okay.
my question to you guys is this: what does this 3 do for us? What's the 3? If you guys,
Shows the period.
in regards to this graph right here, the radius. Awesome. So notice real quick here. Here's your middle. Yeah, that little 3 there. It's this little piece right here. That was a 3 away from the center, and this was a 3 away from the center.
So it doesn't have to be perfect. Okay.
Cool.
So one of them could be 3 and one of them could be 1.
Wow. So if you want to do, you can change it. If you change this to a 2, you got yourself an ellipse at this point, didn't you? Right. If you keep it as 3, you got yourself a circle. Good. It's just that little change there. Okay. Let's jam with it here. So let's go jump to this one right here. Oh, got to move this away. Can't show you the answer. Why am I showing you the answer? That's not a good thing. So all yours here. Example number 3. So eliminate the parameter t from the parametric equations. Whew. Okay. So here's what I want to do. So far, we've been doing something called, this is called parametric equations, right? I want to take this equation. I want to get it back to the x and y function. Or, oh, hold on. We can't make it back to a function. It's not functions, right?
It wouldn't function.
But it's going to be some kind of equation. So remember, these guys are not functions, right? But they are equations.
So how do you put them into one?
I
You
know.
gotta make one.
Absolutely. So if I see a cosine and a sine, I go back to my trigonometric Pythagorean theorems. I say to myself, is there a connection between sine and cosine? Yes, there is. And the connection is?
Is it sine squared plus cosine squared equals 1?
Perfect. I think so. Let me move this down. Let's see if, oh yeah, it hides away down. That's so cool. Sine squared plus cosine squared equals 1. Love it. Okay. And then the only thing we can change here is instead of having a theta, right, we can have a t. And then what we do now, just to make it kind of a little nicer, and I'll see why, we put the cosine first. We're going to write this one first, then the sine. And the reason for it is because we like x's to be first, and then the y's in equations. And notice what happens. Oh, we have a little connection here. So let's do this here. Can you solve x equals 3 cosine t? Can you solve that for cosine of t? What should we do to solve it for cosine of t? Divide by 3. That's it. We good? I see people writing stuff down. I'll wait, and then we can jump to the next slide. But if you want to, can you write x is equal to 3 cosine t? Divide both sides by 3. See what you get. And stop there for a little bit. Then write y equals 2 sine t and solve that for sine of t.
Wait, and then you can.
What? You
This
can
is so
plug it in.
cool.
So it's like 6.3. So is.
But then you can make a triangle.
What triangle? Hold on. 1 second. We'll see.
You
So I go here. Okay, and we divide by 2, is that right? We divide by 2 over here. And we get this. So now the question is, can we plug this into the Pythagorean theorem?
Oh, so no triangle.
No triangle. But Pythagorean theorem says from the previous slide, cosine squared t, is that right?
Mhm.
So what we do is we put a cosine, whatever cosine is of t, we're going to square it. Plus, and then y over 2 squared is equal to 1. Are we good there? Boom. Okay. Think back to your algebra days, algebra 2 days. Do you guys remember what kind of conic section this was? Ooh, did you guys do conic section? Did you guys do ellipses,
We did.
circles?
We did do that, and I don't remember what it is, but I feel like that is a circle.
Okay. So let's go with it. All we got to do is just to simplify it out a little bit more. So what is x over 3 squared? X squared over 9. And then y over 2 squared is? Y squared over 4. Oh, wait, heck no. It is perfect.
Bigger than x. But it equals 1, which means it's like.
So cool. So you guys, if you guys remember from algebra 2, Mr. Grant's class, this should be an ellipse, right? It goes out 3 to the right and left, and it goes 2 up and down because of those guys. Did you guys do those in algebra 2? Okay.
It's just a long time ago.
So, and now this guy is just this guy. So these two are exactly the same. They're just in different forms. We good? So here's parametric form, and here's rectangular form. Okay, you guys talk to me. Anybody from Wednesday? Tell me, why is this right here superior to this?
Just 1.
Say again?
Trigonometric.
So we introduced the t. Yeah, true. And then what makes it so good? What makes it so
It's 1 and not 2.
we can graph it? It's a function, right? And go ahead. Oh yeah, so these guys right here, this is called the rectangular coordinates, right? X and Y. That's the rectangular coordinate system. This guy's called the parametric system. We good? And so remember also last time is t controls how fast you go, right? We can actually go faster or we can go slower, right? Depending how our t changes, right? Yeah, let's do that. Let's do that. So grab your calculators if you guys have some. So grab your calculators. We'll graph this by using that. We good? So let's jam with that here. So let's see. Let's go to here and let's see. I know I can do it like this.
You made a face. I was because I was confused. I wasn't sure about which part.
All right, let's go with it here. Let's see if I need to change this. Let's see. Do I need to change? Yep. I'm gonna change it to a T84. You guys have 83s. That's fine too. It can be very, very similar. Let's go with it here. So first things first, on your calculator, first things first, you got to go to mode because you got to make sure that you are in. Let's do degrees. That's fine. We do degrees. And then we've got to go to par, which is called parametric mode. So you have now switched your calculator to parametric mode. Everything has changed. We're good. So second, are we good there? And please tell me if you need help, raise your hand. We're good. I don't want you guys to get lost. We're good. So, and if you just want to watch, that's cool too. So click second and mode, which is to quit. Go back to home screen. We're good. And let's go to y equals And that has now changed for us. So you, instead of y1, y2, y3, y4, you have now an x and then a y pair. So let's punch in what we have. We have 3, is that right? 3 cosine. And then what you do is you want to go for your x variable, right? But when you click the x variable, it has now changed into a t variable. And then click enter to save it. Next is we're going to do what's 2 sine, right? So it's 2. Dunk, dunk.
Mine's still an X. Is that me?
Let me see. Did you click this variable button?
No.
Gotcha. Boom. That's your variable button. All right, and then 2 sine of t, and click enter and go. Boom. Okay, now what we have to do is for parametric equations, we have to think about the window that we have. We good? So notice we have not moved to the right or to the left because we don't have a plus or minus anywhere here. We're in the center. We have a radius of 3 horizontally. Are we good there? Oh yeah, we'll see. Just a second. Your table. Look at your window. Okay, guys, and 2 sine, right? So let's do this here. Let's make our window. Let's go to window. And we're gonna go, oh, this is a t value here from 0. Now we are in degrees, is that right? So we have to go from 0 to 360. And then the next one is, how often do you want the calculator to calculate? And usually it's like every 10 or 15. This will take a half an hour to draw this. So I don't think I want to do that. So maybe every 10 degrees, I want it to calculate and then connect the dots.
Why is that the default thing? It's so long.
Oh, no, it's always saved from the last time you used it. And the default was we were in radian measurement. Yeah, now we're in degrees. Okay, so my x min has to be a -5. My x max would be 5. And how often do I want my little hash marks to show up? Every 1. Click enter. Y minimum, same thing, because I want to get like a square. So -5 to 5. And then the dash marks to be 1 every time. Okay, are we good there? So -5 to 5 of 1, -5 to 5 of 1. Okay, are we good there? I think we're ready, guys. I think we're ready. We're ready for the graph now. So click on graph, see what happens. Hey, that is an ellipse. Is that right? Now, the only thing is your calculator screen is not a square screen. What happens, it is elongated horizontally, right?
Yeah.
So this ellipse is not really that kind of wide. We good? Yep. So how do we do it? We'll go here. We got to go to zoom. Go to zoom. And which one? And zoom square number 5. Perfecto. And what happens is that is going to make sure the screen that you have is exactly perfectly square according to resolution, not to width. Enter. Whoa, that was fast. Did it just do that for me? Blink of an eye, is that right? Or did I do something wrong? Say again.
Let's click zoom square.
Uh-huh.
Is it zoom square?
Oh, so your window is going to stay the same. So also it's going to be from -5 to whatever the version is. So let's do that here real quick here. So this screen, yes, if you move this out to the right or to the left, then it's going to be off, right? Because it's just staying in position. Did I answer your question? If you go back to window, notice what happens here with the window. Window is now just interesting. It's -7.5, -7.5 to 5. So what does that tell you? That tells you that your horizontal screen, right, is about, let's see, what's 5 multiplied by, it's about 1.5 times bigger on the side than it is height-wise. We're good? That's kind of what it's saying. Cool. So Megan, it's going to keep this same thing no matter what you do. And then if you're off a little bit, then you got to be off. Okay. So class so real quick here. There it is. There is your ellipse in correct way. That's the way you probably want to graph it on your sheet of paper. We good? So in the homework, it's going to say graph this and then convert it to your sheet of paper. All right. With that, are we good? So last time what we did is we did these graphs. So this time what we do is we're trying to convert between rectangular coordinate system and the parametric equation system. Okay, we're good there. Let's jump and do another one. Finish there, finish there. Oh, no, just kidding. There it is. Sorry, gave you guys part of the answer. Can't do that. It's this. All right, class, here we go. So let me just make sure. All right. Let's see. All right, class, here we go. So can you tell me a relationship between cotangent, cosecant? Is there a relationship between those guys?
Square.
Yeah, I think we have. Yep, perfect. So looking at your, if you have your stop here, let's see. Okay. I think that's better. Okay, so let's go with it here. So sorry, had to mess with the technology here. Are we good there? So on your sheet of paper for the Pythagorean theorems, right? You should have found one that connects cotangent and cosecant. That's it. And we're gonna do the exact same thing that we did before, except do you guys remember, even like the last problem, whenever we converted to rectangular coordinate systems, we normally like our conic sections, right? Our stuff that we were doing, we like them equal to 1. So can I convert this kind of over to 1 eventually? Yeah. If I just move over the cotangent to the other side, are we good there? Now we're equal to 1. And then here it is. We like to write this in terms of the stuff on the left side and the right side. So the 1 is on the right side for us. Okay, one more thing we got to do. Is we have to convert it to a t value instead of theta values. Are we good there? Does that make sense there? So that's the form that we want to use. And remember how we wrote this one and we used all the different various forms? Remember that? How we did that? And we had form number 3 when we did those. Okay. So we're writing down, go for it. And now all we do is we do the same exact thing. So now the question is this, can you solve x is equal to 3 cotangent t for cotangent? Can you solve y is equal to 3 cosecant t for cosecant? That's it. That's the easy part here.
So many possible solutions.
So let's go with it here. So how about divide by 3 here? We good there for that one? Divide by 3 here. And then we just plug it in. So that means that's y, that's x. Is that true? Do we have what we need over here? And then we have ourselves y squared over 9. X squared over 9 is equal to 1. Now, real quick question. If you guys remember, what is this form from? I know it's been a year, but do you guys remember what happens if you have perfect squares, but then you have a minus in between them instead of a plus? Because plus makes the ellipse. What does a minus make?
It's like a circle, but flipped.
Oof. Flipped which way?
The same way. Draw the other way.
Mm-mm. No,
Is it a circle?
no.
Is it a quarter circle? That's what I was. That's how I took this. If you have a circle, then just flip it. But no, even friends like that's what I interpreted as.
Uh-huh.
Flip it. Flip it. We have no clue.
All right, let's graph it. Let's graph it on the calculator. Jump to.
No, I saw. I'm not gonna know it. Sunflowers.
I'm going to jump to this guy here, and then let's go to y equals. And then let's see, what do we have for the x again? What was x? X was equal to?
Squared over.
Oh, no, originally, x was equal to what? 3?
3 cosine 2. Or 3 cotangent 2.
Cotangent. Was it cotangent? You guys talk to me here, so I'm going to go like this.
Cotangent. And then cosecant.
We're good. Let me go back just to make sure. Got the right here. Yeah, there it is. It was 3 cotangent x, right? Or sorry, 3 cotangent t. There you go. All right, let's go with it here. So how do you make cotangent on your calculator?
1 over tangent.
1 over tangent. So in this case, it's going to be 3 divided by tangent of t. Boom. Next. What's the next one going to give you? 3 divided by reciprocal of cosecant. Sine of t. Perfect. Okay. This would be interesting. Let's go see if anybody graphs it here. See what you guys get.
It is a backward circle.
Okay. Not a flip circle. It's weird.
Well, that be a asymptote, or do they not
Ooh,
behave?
interestingly enough,
Horizontally,
so
only vertically.
we call this an inverted ellipse. We call it a hyperbola. Do you guys remember? Have you guys heard of hyperbola before?
Keep going.
I heard about hyperbola.
Yeah. So what happens is a hyperbola. This one it turns like this, and it almost like straightens out, and it keeps on going. And these guys right here, if you draw a line here, this would be a asymptote coming across here. Those behave as perfect asymptotes. All right. What do we do with these guys? We model comets. What comets do is they will wrap around a planet. Let's say the planet is like right here. And a comet usually flies straight until it hits a gravitational pull of a planet. So comet's flying straight. It hits the gravitational pull of Earth, right? And it turns around like this, and then it swings out and goes out straight for
That
a
was the
while.
thing that we saw.
Cool, good. That's Voyager 1, Voyager 2, right? This is exactly how to do it. Once you take and slingshot, right? We call it the slingshot effect. It's going to go straight for a while until it hits another gravitational pull.
It just didn't graph the rest of it. It was, oh, that must be like the limit.
I think so, yeah. And I'm sure why you have the lines. It just stopped, yeah. That's right. It would go out to infinity, though, technically. Okay, guys, real quick here. So do you guys remember something called hyperbolas from Algebra 2? So that is the parametric equation of a hyperbola. Okay, let's jam. Next one. The toughie. Can you guys go with this one here from beginning to end by yourself? And then check with the person next to you. Yeah, trying to put this into the rectangular coordinate system, or in this case, the directions on the homework is eliminate the parameter t.
I don't want to do
I'm so sorry. All right, let me help you out here though. Let's see. If I'm going to do the first thing first is I'm going to add 3 to both sides. Is that right? Add 3 to both sides. Now you got 3 cosine of t by itself. And next thing we should do is divide by 3. So how cosine t is equal to x plus 3 over 3.
Or no, because it's an X.
No, yeah, can't pull a 3 because the 3 had to be, there had to be an extra 3 with the x as well. All right, this one here, I'm going to subtract 2 from both sides. I'm going to divide by 5. Everybody okay with sine of t is equal to y minus 2 over 5. So again, what is the relationship between cosine and sine? Bless you.
plus.
It's a plus relationship, right? It's the Pythagorean theorem. And the way we like to write it is cosine squared. That's the cosine squared t, right? That's from the equation that we made last time, right? Cosine squared t plus sine squared t is equal to 1. Cool. Now the question, oh no, one more thing. We got to simplify it out. So what'd you do?
2 longer equations.
So what you do here is you make it into an ellipse equation. And the ellipse equation is x plus 3 to the second power over 9.
You don't have to write out the
So you don't FOIL out x plus 3. So y minus 2 you don't FOIL out. Leave it as there. But the bottom number you want to be the squared value of. Boom. Okay, it's a plus sign. We good?
At the end of the day,
It's a plus sign there, so that means it is an ellipse. And we go from there. Okay, but for the homework, you don't need to graph it, right? You just need to change forms, right? So you just need to change from this form. This form, you're technically done right here. There's no need to graph it. Okay? Yeah, and it's just learning how to change from one form to another. And in mathematics, there's a lot of different forms. And so what happens is you can do the work in one form and then you switch it back to the
ran into the tree.
So sad.
what happened? What happens?
Difficult. It was difficult. I don't know how she managed to do it.
And this one.
Stacked up, and I was like, oh.
Have we ever done the Ferris wheel problem? Yeah, I think we've done this one right here. So now the question is this, can I make it into parametric equations? And so if we go back to our Ferris wheel problem, way back when, I think it was chapter 3 or 4, I forgot.
I'm a fantastic driver.
So, yeah, okay. So class, real quick here, let's go with it here. Let's see if we can actually make this into an equation that works for the description here.
I'm getting driver's license on Wednesday.
So you know how to drive people?
No.
Guys, real quick, let's go. So our Ferris wheel has a radius of 120 feet. If you have a radius of 120 feet, does this make sense right over here? There's 120, goes off horizontally, right? There's 125 here, 125 here, right? And then if it's 125 sine of t, that means it's your radius to go vertically. We good? So isn't this kind of cool? You're looking at a Ferris wheel, and right away you can actually make the outside edge description of it. Only thing we got to do is this. You have to make it sit 4 feet above the ground. Because remember with Ferris wheels, you always have to like walk up some stairs, right, to get there. All right, and then also we're going to look at the time factor now. We're going to have to figure out a time so that one trip takes exactly 20 minutes around. So we're going to actually include the time factor into this.
They should make Ferris wheels that cut into the ground instead of above them.
So let's go with it here. Let's see if this makes sense. So are we okay with the 125 though, right? Whoa, a little too fast here. So real quick here.
Just want to talk about different Ferris wheels compared to the size of skyscrapers. Isn't that a thing?
We did that one. Yeah, we did that. So here's what we do. And so what we got to do is we have to move this up so many units. So if it's 14 above the ground, we have to make our center.
You didn't do that, the center would just be the
Yeah. So the middle of it is actually 14 above the ground, but we want the bottom of it So we're gonna add 125, and then we're gonna add 14 more. We did there. So that just made it to be 14 feet above the ground as the minimum value. Cool. Okay. I thought this was a fun problem here from the textbook here. I kind of copied and pasted. Okay, now what we got to do is this. We have to move this so it's so many feet away from the booth. So notice what happened was since we moved it up and down, we worked with the y coordinate. We're good? Now if we're going to move it away from the ticket booth, we're probably going to use this guy over here.
Regular wrapping,
Mm-hmm.
it's in different parts. You know what I mean?
So now let's see. Uh-huh.
Yes.
Yep, absolutely. Parametric regions are super cool. So we have now, if it's 200 feet away from the ticket booth, we don't need to add in the radius because the radius is not a factor in this way, right? Okay. So if we move it 200 feet to the right, all we do is we add 200. Now notice real quick how the book writes it. It likes to write the vertical aspect first and then the trig function. You can write it the other way. I prefer writing it the other way because that's the way we learned actually transformations. So are we good there? Is that pretty cool stuff? So we can move things out and in really, really quick here with parametric equations because we're doing one piece at a time. All right. So again?
So you're supposed to write it the other way, like annotation, like you're supposed to put like X's and stuff first too.
Doesn't really matter.
Sometimes.
Depends.
Not
Yeah.
matter.
No. Unless it's coordinate systems, that's all. Yeah. All right, one more thing to do. So now the question is this. Can you convert this real quick here on your sheet of paper as you're doing notes? Can you solve this guy for cosine of t? All we're gonna do is we're gonna, yeah, go ahead, Megan. I'm gonna do it right now. All right, so if we want to write it in rectangular coordinate systems, right, we would just subtract 200, divide by 125. There's your coordinate system for it, right? So that's cool. So we can actually change both around, right? So now let's do the 20 minutes. We want one revolution to take 20 minutes for us.
Half the time when you say revolution, I think of like political revolution, French revolution, and it's just a kind of
Not a trigonometry class. Uh-huh.
There's still some on this. I'm going.
Oh, move this up. So let's go with one item here. So do you guys remember doing this right here?
Yes.
So here's what we got to do. I can write it like this here. So fun little stuff. So far, remember how we've been graphing these? There it is. Remember how graphing it the first time it started right here? Right? But normally if you get on a Ferris wheel, you start right here. True? So in order to move backwards this way, all we got to do is subtract pi over 2. Are we good there? We're just taking a quarter of a circle back.
It just changes the starting point.
It just changes the starting point.
Then how did that change to a rotated? Oh,
You shouldn't.
never mind.
Okay.
Circle, does it matter?
See ya.
Does it matter?
If you do a full circle, no, except for a Ferris wheel, right? We don't really put people on the side, right?
Just for the sake of it being Ferris wheel?
Yeah. So we're just trying to create a model of the Ferris wheel. That's what we want to do. Okay, then this part right over here, guys. Do you guys remember this? Remember how I used to solve for the period of things, right? Remember it was how do we solve for the period of things here? Do you guys remember?
It's
2
cycles
pi
over seconds.
Yeah, it was 2 pi, right, over t, right?
T.
In this case, so since one trip takes 20 minutes, we can write our equations in terms of big T by using this little value right here. So I want the full trip, I want the full time to take 20 minutes, right? As a part of the trip to go one full revolution. We good? So the 20 and the 2 pi line up. I think we're almost done. So if that's the case, everybody okay here? Everybody okay with solving for little t, which is multiply by 2 pi on both sides? And we get ourselves little t is 2 pi over 20 big T. And reduced would be what? Reduced would be pi over 10, is that right? Pi over 10 big T. Now, that big T stands for, right, our time value, right? That's our value for. And so I'm going to give you the final answer here. There it is, which is pretty cool, guys. Real quick here. We have just, again, this is kind of like, this is the last problem, right, of the last section of the chapter, right? This is kind of a little bit more involved than what we started off with in 6.1. So, but here it is. We have made a very, very accurate model of the rotation of the Ferris wheel, starting at the bottom, right? Rotating, and it takes 20 minutes rotating. And then we even got to the fact that how far it is away from the ticket booth as well. Like all those pieces have now been put in place, which I thought was super cool.
Now, what do you do if they want to do multiple times around the Ferris wheel?
Oh, you just keep on going, right? So then the question is this: do you guys remember? So not remember, but when you get it on a Ferris wheel, right? The person usually is not pulling the lever to slow down, go up. Sometimes, right? He'll just turn it on, right? Once everybody's loaded, right? And so notice, especially, well, he'll turn it on and it'll just spin and it'll stop at a certain point, right? But then it's counting the number of revolutions for things, right? Or it's counting the minutes where it started completely, right? I'm thinking more so like other rides where you start something, right? And then it changes direction at some point, right? And then changes another direction, right? And it's all electronically controlled at that point, right? In order to make the ride seem a certain way. Okay, we're good there. So I love this. This is super cool because we actually made a realistic model of the rotation of a Ferris wheel.
I feel like if it's going to be on the test, I might need to review the 5 or 10 thing a little bit. I didn't
Gotcha.
know.
For the period itself. Okay, gotcha. I'll keep that in mind as we do the review. All right, and if we were to graph it, it looks like this. So now, let's see. Let's see. Second here. Yeah. Let's see. How much time do we have? Anybody? When are we out of here? 15 minutes? Yeah.
15 minutes, yeah.
Okay. Let's see. I want to do this instead here. Let's see. If you guys can you guys do this here? Can you graph this on your calculator? That's what I'd like to have. So just try it on the calculator. And let's see, we are in radian measurement now, right?
The calculator.
It has gone missing ever since Monday, I think, or Wednesday.
I literally saw it like 30 seconds.
Oh, really? That's what you think.
Oh, water?
Why? Can I borrow your calculator?
Not a big fan.
If you didn't get to it, sure.
Oh. So you have calculator stuff on the test?
I do not know yet. I'll be making the test during spring break. How about that? So I'll know afterwards.
Just wanted to know, because I have a different type of calculator, so if I want to be on the Monday or the Wednesday, video.
As far
we
as
get back from spring break.
oh no, Wednesday. Yeah, we'll do a review on Monday. So yeah, it'll be bad too. Sorry, class. I'm going to change direction here on you guys. We're good. I'm going to change direction. If you guys want to graph it, try it. Sorry, what? Just because of time. I'm going to get to this one here as well here because I really.
Answer like this.
Sorry, I'm changing my mind on it just because we don't have time for it. I want to get to the human cannonball as well. Yeah. So let's go this way. So again, now let's add gravity. Anybody seen this equation before anywhere? Yeah. Where?
Yeah.
Yes, And have you guys did this recently in physics or?
Yesterday.
Yesterday. Oh, how funny.
That's on this.
It's great. We just did spring. I forgot. No, because we just did springs.
Okay.
Yeah.
Gotcha.
Simple harmonic.
We did.
It's interesting.
Oh,
Sometimes it's a lot of alphabet and a lot of like.
A lot of
You did that. You did that angle too. I just say, well, you could do it at a 45-degree angle. I have that still actually. I don't care about that.
So if you guys want to write, if you need to write these down, let's go for it here. So this guy here is,
We can be using.
can you guys tell me? Yep. You got this one here to do and this one. In fact, if you want to, you can write the bottom equations because that is gravity based upon Earth, right? Since we're not going to launch a human into the moon yet. So if you want to write down the bottom two equations. So here, the horizontal parametric equation is the magnitude of your initial velocity. That's what these guys mean. That 0 means initial, V means velocity, and the bar line just means the magnitude. How fast is the bullet or the human got fired out of a cannon? And it's cosine of theta. And notice real quick, it's multiplied by t all the way at the end. So it's a multiplication here of all this first.
Air resistance.
Ah, that's usually not in pure mathematics. It is, yeah. The T. Uh-huh.
I'm just. So like.
We don't believe in air resistance.
It doesn't sound It's physics. Well,
Do you
there's no air resistance, there's no friction, nothing ever stops moving.
Well, there is friction, but like.
Sometimes. In some equations.
But air
There's no
resistance.
Air resistance, no.
Okay.
You just don't do it.
Then are you actually learning physics?
All right, so let's go with it here. Let's see. With the time remaining, I guess we're gonna get to homework questions next time. So class, let's finish up real quick here. So everybody got the two equations written down? Let's jump to this right here just to visualize it here. So here's your projection. And notice horizontally, it's going to come across, right? On the vertical aspect, what's going to happen is it's going to go up and then eventually it's going to have to come down because of gravity, right? So that's why the 16t squared. And then, so neglecting air resistance, the only force acting on the human cannonball is the force of gravity, which is acceleration of 32 feet per second squared towards the Earth. So we good? And so we simplified, we technically just multiplying speed times time. That's all we're doing. And so going over here, we want to graph the path of a human cannonball if the initial velocity out of the cannon is 60 feet. I'm sorry, 60 miles per hour. And then we have an angle of 30 degrees horizontally. Yes.
Last year.
Let's get this on.
Did you do one in the lab? Oh, that is so fun.
What do you mean last year?
Oh, will we not do this?
No.
It's interesting.
I want to show you, as I do it the trigonometric way, right? See if it's a little different. We good? So first things first, yes, we have to convert things into metric stuff. So miles per hour, we have to use into meters per second. So I got to go into, this is a fast way to convert it. Oh, sorry. Is there a fast way to convert it in physics?
Just the.
Usually we already start a meter per second.
Yeah.
Gotcha. Okay.
So
We can convert, it's like,
a hassle.
there's always so much equations. Like,
So hold on. The physics equation that I gave you guys was in what? Oh, that was in feet per second, right?
You could stitch one of them.
Uh-huh.
We get the same answer, right? It's just the same.
True.
Yeah.
The second half. I wish I would have said two, but
Perfect. So I'm just converting into feet per second. We good? And let's see, time-wise. Okay, 7 minutes here. Let's see if we can get to the end here. So are you guys okay here? So I just have to convert to feet per second because my formula is in feet per second, right? And if you're in metric, there'll be a different formula if you're, right? So there it is. Using, do you guys remember this? Is this called dimensional analysis or no? Do you guys remember this? Or did you guys have chemistry before? Okay, did you guys ever do this converting from like one stoichiometry? Okay, that's what it's called. Gotcha.
that's fun.
Raise your hand if you liked chemistry. Raise your hand if like chemistry was like, that was the
I
bomb.
was so good at that.
I wish I would have done honors chemistry.
Okay, okay, cool.
That was great.
We're doing electricity.
She's actually very.
Shocking.
No, I'm
So here's our two equations. Let's go with it here. So our x equation is 88, right? Because that's the magnitude of how fast you're getting out of the cannon in feet per second. Cosine of my angle and all of that times t. Are we good? And then the y equation is going to be exactly what it is. So velocity, sine of 30 degrees of t,
Yeah.
And then we just have to put in the 16t squared into it.
Maybe get 6.
That is the gravity constant, 32 feet per second.
What is
Right down?
88 times root 3 over 2?
Say it again.
What is 88 times root 3 over 2? Someone with a calculator.
Like
44 root 3.
Yes. I don't know how I didn't think about that like that. Okay.
Okay, so here's what I do. In 5 minutes or less, I want to know the maximum height
Yes.
the guy reaches, the distance that the person is going to travel, and the time in which the cannon hits the net.
The maximum.
Yeah.
Oh, cool. How do you get to the maximum height?
I use the equation.
Charging. Oh no.
Velocity final box.
White.
Yeah. What is that?
I like
Wait.
when you just turn it.
There's an
what
even
is
inside
squared
of that. You
plus
need to
two.
get rid of it.
Yeah.
Acceleration
The
of
little-
y
little
times distance.
something.
Interesting. Okay, so let's do, I'm going to do mine in a totally different way then. Okay. So class, real quick here, let's do this here. Grab your calculators now. Grab your calculators and let's see if we can put this into our calculator. So go to y equals.
Can I use it?
Why?
Because I want
So this is going to be 88. And is it cosine, right? Cosine of 30 degrees? All right, and then I'm going to multiply it by t. Are we good there? So notice the t is on the outside of this. Enter. This would be 88 sine of 30 degrees times t minus 16
Yes.
t squared. Are we good there with just plugging in the values?
Yes.
Okay, so now the question is this. As we're looking at this here, so I am, how high is this person initially starting from?
0.
The t is equal to 0, right? We have a time factor of t, right? So let's graph it. Let's see where we're at real quick here. But in terms of, let's see, the person is, velocity is 88 feet per second, right? Has an angle. Looks like we're starting at 0, right? And the person going up and then comes back down, right? So let's go with, let's just try some windows real quick here. So window, 0. The only thing is, let's see, our t step, that's in terms of time, is that right? Because it's feet per second. So think about how many seconds this is taking. So I'm going to go with maybe like, I'm going to go 400 seconds. Let's see what's happening with 400 seconds. And I'm going to go every 10. So my x min is going to be 0. My x max, maybe, I'm going to just draw 250. We good? Uh-huh. Enter.
what?
I think that's
I know.
All right, and then the y min is going to be 0, and then I'm not sure like the height. How high is the person's going to go? I'm just going to put in 250 as well, just to sort of see initially. Good. Okay, and then each of the tick marks that I have is going to be 100. Those are 10. Okay, so
88 cosine 30.
the way I have it here is I have a window of 200, 200 each side, 250 each side, right? And I'm going for 400 seconds, which is what? That's like 2 minutes.
Judging how much time it would take for him to.
Yeah, shoot out and come back down.
It's more than 2 minutes.
minutes.
It's almost
4 minutes, yeah, okay.
That's a lot of T.
That's a lot of T.
Yeah. So the time I got 4:45 seconds.
Oh, gotcha, okay. So way off, right?
Of air travel.
Okay, so then let's go to 4 then, right? Sorry,
Do 5.
No,
Let's
do
go.
5.
I'm gonna go 10 real quick here, just real quick here. And then every 10th of a second, I'm going to, oh, gotcha, we're good there. So there's the human cannonball. Boom, okay, so mine was 250, so it's like somewhere here, we good?
177.
Oh, awesome, okay,
So 171.
sweet.
Still even looked up yet.
Projectile, it is a projectile, so it's not a semicircle, it is a projectile motion, it goes like, gonna go down.
So-
Yeah, so if it's gonna go, he's gonna go underground, he's gonna go way underground for a long
I
time.
saw for that.
Self up, self down.
Sweet, okay, so real quick here, since we have a graph with 3 minutes left, can I figure out the maximum value it reaches right here? So
On top of the one.
Yes.
Uh-huh. So I'm gonna go like this. I'm gonna go to calc. Whoa, that was a different calc here. Hold on. So graph, we're here, is that right? That's what you guys get when you click on calc. Is that what you guys get? Oh, interesting. Okay. Never mind. Never mind. It works a little different there.
No problem.
It's like down it under 90, the distance it goes or something like that.
It looks like 29.35
Sweet. Okay.
to the little area.
Gotcha. So if you trace it, right? So if you trace it, let's see what happens here. So there's my little trace. You know what? I don't like the fact that there's like so much space up here, right? So I'm gonna cut it down to like 60. We good? Or 50? Let me cut down my, because this is a whole bunch of wasted space up on top. So window, I'm gonna move my Y maximum, not 250. That's way up high. So let's go to like, let's go 100. Let's see, we're at an 100.
It should be pretty close.
30.24.
Nice. Okay. So I see even half. Well, let me go to 50. Let me go 60. We good? So how about just 60 maximum height? And let's see. Okay, that's a nicer graph. We good? There's a human cannonball guy. Yeah, we'll stop here because I did want to show you the video of it. So how about this guy? This is where we finish off with before vacation. The human cannonball event. No, it's just a
Mr. Jim, I have a question. Just save them first after the break.
yeah, absolutely.
Oh, no.
This is not just a man.
Sorry, why once we don't do the
Oh, it's all
hard is not,
Yeah.
but yeah,
Oh.
I keep on extending that one, but then
That's true.
Hey, that looks
so the ring of fire.
Honestly,
Why is he swimming?
Oh, he almost missed it. He was like towards the end of that net.
Oh, that is.
I don't think.
That is awesome. I would never do that, but I would watch
Can you
it.
imagine if you like screwed up and went like a foot too far and just died?
Well, it's just.
Like, that would suck.
You guys want to give him a fight?
Regular.
Yeah, how is it not a Friday? That's insane.
Yeah. It's two. I keep expecting a break. Thank you. Yeah, no, literally. I was going to go home.
So class will handle homework. We finished up 6-4. We'll handle homework questions after.
I don't. I was gonna go home.
Oh, yeah. Please don't turn in any homework until we go over homework questions.
Thank you.
Enjoy your vacation, guys. Yep. Thank you. Bye. Bye. I mean.
And I was like, I need to go do the test.
It's right, yeah, first year, there was some.
So this movie, right? So just. Like all the adrenaline going on.
Oh, she's, exhausting. Yeah.
So, and then I'm basically just be driving around the entire week next week.
Where to?
Anywhere.
Anywhere? Okay. Oh, gotcha. Okay. Uh-huh. Sweet. When are you planning to take the test? Ish.
It's probably here,
Okay.
so I wanna try to master. Onto the highways first.
Yes, correct.
I've only gone on the highway twice, so
Uh-huh.
it's terrifying.
Oh, yes.
But I don't like it.
Absolutely.
I drove myself to and from work the other day. Granted, I did take like the main street through town, but I still got there. So
On beat.
it's just practice. Remember, trying to go out almost every single day and it been here for like about 100 years. And it's normal to be absolutely terrified of it when you first start. So, I already am.
Yeah.
So,